Good morning, my name is Craglia. I'm an analyst at the International Transport Forum, and today I'll be presenting our latest analysis on decarbonising Europe's trucks. Just briefly, for those of you who don't know about the International Transport Forum, we are an intergovernmental organisation with 64 member countries around the world. We are housed at the OECD in Paris, and we act as a think tank, both collecting statistics and carrying out modelling, as well as writing research and policy briefs, as well as convening different stakeholders, policymakers from our member governments, as well as industry and academia, in a variety of different formats and workshops. The other thing we do is organize the largest annual gathering of transport ministers in the ITF Summit, which is typically held in Germany. So the research that I'll present today was carried out as part of the ITF Driving Implementation Actions project. This project was funded by the European Commission for 2 years and aimed to help decarbonize the so-called hard-to-abate sectors, so aviation, maritime shipping, and heavy-duty road freight. And to do this, we organized 3 parallel working groups with different governments involved, different companies involved, all to help decarbonize each of these sectors. So this slide shows you the technical level participants that joined from our member governments for the road freight group, as well as companies and NGOs and academia that aren't shown here. So this report was published in September 2022 and had an aim to investigate the total cost of ownership of different zero-emission vehicle technologies and how they might be able to decarbonize trucks. So the aim was to understand the economic feasibility of these technologies and understand which is most likely to reach parity in costs with conventional diesel vehicles, understand when that might happen and how this might differ between different vehicle size segments in Europe, and finally understand what degree of certainty can be placed in the results and how this uncertainty might be reduced. So we investigated the total cost of ownership of 4 different powertrain technologies for road freight. The first being conventional diesel trucks, understanding what their cost of ownership is today in the different size segments and how that might change in future scenarios. We then also looked into 3 zero-emission vehicle technologies, I guess the more prominent and highest technology readiness technologies. The first of these includes battery electric vehicles with relatively large batteries, which could be charged either in depot, overnight charging, or with high power charging en route. The second one are vehicles that can use catenary electric road systems, pantographs. And the third technology, zero-emission vehicle technology, are hydrogen fuel cell electric vehicles. And so we investigated those 4 different technologies for 9 different vehicle size segments in Europe, ranging from relatively small 7.5 ton vehicles, as you can see in the bottom right. These only account for a relatively small share of sales in the heavy-duty road freight sector in Europe, all the way up to larger vehicles, including tractor trailers, which you can see in the top right, account for over half of vehicle sales in the heavy-duty road freight sector. So by investigating these different types of vehicles, we hoped to understand a bit how these different zero-emission vehicle technologies could be adapted and which is likely to be cost competitive and in which size segment. And it's important to understand this because the operational requirements and also the technical characteristics of trucks differ. So you can see here on the left, the average daily mileage of trucks varies quite a lot. The smaller vehicles tend to travel less, shorter distances every day than the larger tractor-trailer vehicles. And similarly, they have different power, different weights, constraints. All of these can influence the feasibility of zero-emission vehicle technologies within each different vehicle class. So typically in past studies that have tried to estimate the feasibility of different technologies for decarbonizing trucks, typically they have used scenarios of the future, and scenarios are useful as a way of testing different assumptions and seeing their impacts. However, I guess the downside is that sometimes scenarios can be quite sensitive and quite potentially biased to the assumptions that are made when making them. I'm sure we've all come across scenarios in the future that have particularly perhaps low hydrogen costs or particularly high diesel costs, different factors that can potentially influence the findings and the results. So part of the novelty of this analysis is that we aimed to be as unbiased as possible and explore a range of different futures. And we did this by setting an optimistic and a conservative bound for each of the main factors and the main variables that influence the total cost of ownership of different technologies. So you can see here on the right, different factors that we used. For example, figure I, which looks at battery pack costs, we have a relatively optimistic case of battery cost reductions over time, which are in line with historical trends and future technology deployment. While as we also have a relatively conservative case in which battery costs actually increase in the short term due to limited supply and very high demand for batteries, with then a steady decrease over time. The aim here is to try and at least reduce the level of potential bias in carrying out these analyses. And we do this by, for each variable, taking that optimistic and conservative bound and randomly generating scenarios for each of them. And so we therefore explore 1,000 different scenarios for each technology and each vehicle size segment to understand the total cost of ownership of each technology. Taking those 1,000 scenarios and using them in our numerical model, these are the results. So these graphs show the share of the heavy-duty vehicle market that each technology could theoretically attain by having the lowest total cost of ownership. So on the left graph are internal combustion engine vehicles, so diesel vehicles. In the middle are battery electric vehicles, and on the right are hydrogen fuel cell electric vehicles. And this figure excludes electric road systems for now. And what we can see is that on the left, in 2020, almost all heavy-duty vehicle sales are likely going to be cheapest with diesel vehicles. So 100% of heavy-duty vehicle sales are going to be cheapest with diesel vehicles. However, over time, with technology improvements and economies of scale, we think that battery electric vehicles will become cost competitive in the near future in the majority of applications. Hydrogen vehicles, on the other hand, on the right, could potentially become cost competitive in certain scenarios. However, these are relatively niche edge cases that are very reliant on very, very low hydrogen costs, so below 2.5 euros per kilogram at the pump, as well as relatively high costs for other factors such as batteries and electricity. So from this, we conclude that hydrogen fuel cell vehicles are unlikely to be cost competitive for the mass market. These graphs show the sales share that will be cost competitive over time without any government financial incentives. Important to iterate that. What you can see in the middle is that there's a relatively large amount of uncertainty of when vehicle technologies will become cost competitive. Some of the key factors here are electricity costs and diesel costs. These two factors explain a fair amount of that uncertainty. And what we see is small truck segments are likely to become cost competitive first. So you can see here in the early years, there is some adoption of battery electric vehicles. However, these don't account for a very large share of sales of heavy duty vehicles, as I showed before on the table. So the smallest vehicle size segments only account for around 5 to 10% of sales within the sector. The larger truck segments are likely to become cost competitive afterwards. And because they account for a very large share of sales, we therefore see this large jump in the share of the market where battery electric vehicles could be cost competitive. Now, I'll iterate here. The costs of infrastructure are included and payback periods are included within it. And these graphs, as I mentioned, showed without any policy incentives and excluded electric road systems. If we now include electric road systems as a vehicle technology, we only look at their adoption after 2030. So we don't look at the period of scaling up or of infrastructure deployment. But hypothetically, if electric road systems were operational by 2030, they could actually attain the majority of the truck market and could potentially be even lower cost than diesel or battery electric vehicles. There are some uncertainties here that are included, such as the costs of infrastructure is quite uncertain, but that's included within this. There are some uncertainties about the level of utilization of how many trucks would be using these vehicles and how that scale up might proceed over time. But with those uncertainties, there's still likely to be a very significant cost competitive case for electric road systems over time. We model that they can't be used in all road freight sectors, which is why you see that they don't obtain 100%. Here, some of the key uncertainties are on the financing of electric road systems and the payback periods. This we don't get into too much, but could have quite an impact on the results. So the graphs I showed you before don't include the impact of any financial incentives or policy measures. So that graph on the left is the one you saw before for battery electric vehicles. However, a range of different policy measures could reduce the uncertainty involved in the adoption of zero emission vehicles and shift the year in which they become cost competitive to earlier years. So you can see here that different policy packages such as zero interest loans that can help with financing costs, purchase subsidies or carbon taxation can all help to reduce that level of uncertainty and accelerate the adoption of zero emission vehicles. From these findings, we therefore distilled 6 policy recommendations. The first is to ensure that policies to promote the direct electrification technologies, so battery electric vehicles and electric road systems, in trucks remain technology neutral or as technology neutral as possible and avoid closing the door to either of these technologies. This is important given they both, at least on paper, have the potential to be cost competitive for the mass market, and further studies are needed to understand their relative benefits and flaws and how they may well also complement each other. Particularly for electric road systems, there are some uncertainties around its financing and the timescales involved in its deployment. So we therefore recommend launching targeted studies and pilot projects to understand their merits. For particularly challenging road freight applications, we recommend also further studies of what technologies would be best applied. So not all road freight applications will be able to be directly electrified, particularly long-range applications or sparsely populated areas which don't have sufficient truck traffic are likely to prove particularly challenging. And it may well be that other technologies, potentially also including hydrogen fuel cell vehicles, may be better placed here. Next, we recommend introducing policies that help kickstart those economies of scale and help zero-emission vehicles become cost competitive sooner, reduce that level of uncertainty and accelerate its adoption. Next, accelerating the deployment of the infrastructure for zero-emission vehicles. And finally, strengthening regulations such as CO2 emission standards that can help accelerate the deployment of trucks and make them more energy efficient. That's all from me. Thank you very much.